It should be clear to you by now that we actually require two voltage supply, one for creating inversion layer and the other for providing path to the charge carriers present in inversion layer. However, it is observed experimentally that when the gate to drain voltage difference is greater than thermal voltage, the drain current increases linearly with the increase in drain to source voltage difference. But as gate to drain voltage difference becomes equal or smaller than threshold voltage, the current begins to saturate and becomes nearly constant. Depending on these conditions, the MOSFET is said to be operating in triode or linear region and saturation region. After little bit of modification, we can change the conditions for triode and saturation region in terms of drain to source voltage difference and gate to source voltage difference. Gate to source voltage difference minus threshold voltage is an important parameter which is commonly referred as overdrive voltage. When the MOSFET is operating in triode and saturation region, then there is a significant difference in the shape of inversion layer. Consider the p-test substrate MOS capacitor with gate to source voltage greater than threshold voltage such that the inversion layer is already present. Initially, when no drain to source voltage is applied, the charge carriers in the inversion layer are more or less distributed in a rectangular fashion. But as we increase the drain to source voltage, the distribution pattern for the inversion layer changes and begin to look like a trapezium. This happens because the positive voltage on the drain attracts more of the electrons present in the inversion layer adjacent to the drain terminal. There is a special case when gate to source voltage minus threshold voltage is equal to drain to source voltage. In this case, the inversion layer looks like a triangle. The positive voltage on the drain is sufficient enough to completely exploit the electrons present near the drain terminal. This particular condition is referred as pinch-off condition, and the corresponding drain to source voltage is referred as pinch-off voltage. Observing carefully, you will realize that both overdrive voltage and pinch-off voltage have equal values, but they have totally different definitions. If we increase drain to source voltage even further, then the tip of the triangular inversion channel begins to move away from the drain. This is because the high positive voltage on the drain begin to attract charge carriers in the inversion layer even though they are far away from the drain terminal. In terms of shape of the inversion layer channel, we can say that when the inversion layer channel looks like a trapezium, then it is said to be operating in triode region, whereas when the inversion layer channel looks like a triangle, then it is said to be operating in saturation region. The inversion layer channel is said to be discontinuous in saturation region, but this is not a point that one should take literally, as obviously there is a very thin channel which will be present between the tip of the triangle and the drain. But it looks like as if the channel is no longer in contact with drain. So we have two regions, triode and saturation region. But till now we have assumed that the overdrive voltage is equal to or greater than 0 and the drain to source voltage is always positive. But what will happen if this is not the case? There is a third region which is referred as cutoff region, which occurs when either the overdrive voltage is negative or the drain to source voltage is equal to 0. In the triode and saturation region, both the conditions are necessarily required. However, in cutoff region, if any of the condition, whether it is of overdrive voltage or drain to source voltage is satisfied, then the MOSFET is said to be operating in cutoff region. When the overdrive voltage is negative, then there is no inversion layer. When the drain to source voltage is 0, then the charge carriers in the inversion layer does not have a path to flow. In both the conditions, there is no current at all. Now, consider the case when the drain to source voltage is negative. In this case, the drain will act like source and the source will act like drain. This is because we know the MOSFET is a symmetrical device, and if the polarity of the drain to source voltage is negative, then the electrons, rather than moving towards the drain, will move towards the source terminal. If we have to conclude the two devices, BJT and MOSFET altogether, then we can say BJT is having 3 terminals and 4 operating regions, whereas MOSFET is having 4 terminals and 3 operating regions.